Welcome to solverfy.
So for this problem, kind of complicated. You have a wire creating a magnetic field, and it's a spatially dependent magnetic field, and you have a movable, so you have like a loop with like a movable piece that's moving at a velocity, at a particular velocity. And so first you want to get the EMF through the loop. I'm not going to fully draw the picture. It would make this video a lot longer than it already is going to be, but you can see in your book. So the wire creates a magnetic field that spatially varies, and the formula for the magnetic field is mu naught I over 2 pi r, where r is the distance from here. I'm going to use a coordinate system, the one that I have burned into my memory from multivariable calculus. This is my coordinate system, into and out of the page is x, and the plane of the page is z and y. So first, let's get our ultimate goal is to get the EMF, and we do that through Faraday's law, which means we need the flux. And so let's first get an expression for the flux. So it's going to be the integral of b dot dA, and b is mu naught I over 2 pi. And then this time, in this case, our radial coordinate is going to be along the z-axis. So 1 over z, and then our dA is going to be dz dy. And so this is a double integral. Let's do z first. So mu naught I over 2 pi times the log of z. And then actually we want to evaluate this integrand from a to L. So I guess I'll go ahead and label that here. So here's a, and then this thing's L. Oh, okay. I realized I made a mistake, but it's not a fundamental mistake, but just a little mistake. So we're evaluating this integrand from a to a plus L. So it's going to be L plus a all divided by a. And then we integrate over dy. That's just going to be whatever the width is. And to get the EMF, we want to evaluate how this is changing in time. And actually, let's just work in magnitudes. Don't think we care too much about directions for this problem. And the derivative of that, the only thing that's changing is time is the width. So that derivative of that is velocity. So then we'll have mu naught I over 2 pi times, the log of L plus A over A. Now it's times velocity because we took the time derivative. So I'm going to revise my calculation, but it's a super quick revision. So I'm hopefully all good. So let's see. Mu naught 4 pi times 10 to the minus 7. So mu naught times I is 100 times the velocity is 5 times the log of this thing divided by 2 pi multiplied by 5. Let's see what I get when I do that. Okay, mu naught I, the logs, mu naught, and then I is 100. Oh, I multiplied by 5 twice accidentally. Okay, great. So when I do that, I get 0.0023 or 240. Oops. Okay. Difficulties beget difficulties. Let's just erase this, make sure it erases properly. Okay, without further ado, 0.00024 volts. Okay, so that's A. And then for B, what we want to do is find the current. So I is E over R. And then, so we want to divide by the resistance, so 0.00240 divided by the resistance is 0.4. And with that, I got 0.000599 so 0.0006 basically. Amps. And for C, I'm asked to calculate the power, so that's just going to be the EMF squared divided by the resistance. So I'm going to redo that calculation as well. So that's 1.44 times 10 to the minus 7. Watts. And then for D, we want to get the force. So force in DF is going to be I dl times B. Everything's all perpendicular, so I'm not like going to include the crosses, but it's dl cross B usually. B is changing with L. L is along the Z dimension, and so we need to integrate our B along the Z dimension and multiply it by the I, and this is the I induced. Because we want to know the force that this induced current experiences. So integrating that, we want to integrate the B field mu naught I over 2 pi R times I induced dz. And then I guess this R needs to be Z because this is the Z dimension. The Z dimension is the radial dimension. And then same integral, I've done it before, mu naught I over 2 pi times the ln of A plus L divided by A. And then I have to reevaluate, that was just our B. And then I need to multiply by I induced. Great. And so redo that calculation. So that looks very similar. How is it actually different than the EMF? So the EMF has this velocity in it, mu naught I log mu naught I. So it's like instead of velocity, I change that to I induced, and it's all divided by 2 pi. Okay. And then I induced, I obtained was what? 0.006 amps. So 0.006. And then, wow, that gives me a very small force. Just sanity check that. It seems way too small. So, I still need to keep the I. Oh, right, I needed to replace the velocity, not the current. Oops, okay, times 100 times And then I need to cut this 0.4. Okay, so with that, I get 2.88 times 10 to the minus 8 newtons. And then for E, I want to find the derivative of the work with respect to time. So that's going to be d by dt of the integral of f dot dl. This time we're integrating along the direction of force, which is along the y direction. And so that's just going to be d by dt of the integral of the force dot dy. So that's just, the force doesn't depend on y, so that's just d by dt of force times y. And then y is changing at a rate of velocity, so it's d by dt. Oops, no more d by dt. Haha. Okay, so it is dy dt, which is velocity time, so it's force times velocity, which I guess is a formula that's come up before. And so now I can, to get that number, I'm going to use this force, is 2.88 times 10 to the minus 8, and then I'm going to multiply it by 5. So that's 1.44 times 10 to the minus 7. Watts. I'm just going to double check something. Great, that looks good. And yeah, so there's that problem.